Mm. Okay, so in today's sessions, we are going to learn more about partial molar properties. Hmm. So we have, as of now, till now, we have learned various equation of states like Van der Waals equation of state, Peng-Robinson, and all those equation of state. Those were basically we have till now used for pure components. Whatever till now we have dealt, it is with pure component system only. So now when we are dealing with mixers, let's say I am having a mixer of CO2 and CH4, or two components or three components mixer, then this is my original Van der Waals equation, that T plus A by V square V minus B is equal to RT. So A is my interaction parameters and B is volume occupied by a single molecule. So when I'm dealing with mixer, then how to deal with this A and B parameter, how to take account, how to take into account these A and B parameters. So for that, first we will be learning about mixing rules. So what is mixing rule? Rule is something that mixer constants in terms of pure component constants. So this B is nothing but basically the size. It describes the size of the molecule. So how can I when I'm dealing with mixer? So there are two ways to describe the mixer property of Bm. So one is Bm raised to 1 by 3 summation of Yi Bi raised to 1 by 3. So this basically gives that you have two components CO2, CH4. So just take the mole fractions of them and you have Bi value of each pure component. So just do this Yi Bi raised to 1 by 3. So what is this assuming? This is basically assuming the additivity of diameters. It assumes that we can add the diameter. So it is, that's why it is coming out to be Bi raised to 1 by 3. And similarly, if we assume that volumes are additive instead of diameter, so it will be just Vm is equal to summation of I YIBI. So these are mixing rules for adding size of the molecule. Similarly, but size, more than size, the interactions correctly inputting interaction parameters is more important than size of the mixer molecules. So for that, this AM term is very important. So there are many ways to many ways how we define interaction parameters A. So AM one way is summation of I summation of J Yi Yj Aij. So this Aij, for that we use combining rules. So combining rule, there are two molecules, CO2, CH4. So two ways of defining the interaction. So one is like geometric mean and one is arithmetic summation. So Aij can be written as Ai plus Aj by 2. So we just take the average of the interaction, or we can just take the geometric square root of Aij. So these are two ways of defining interactions. So then when we define Aij, there is no particular rule that you have to use this or you have to use that, but you have to figure out in which system, which in particular system, which of this combining rule works best. Then I have my Aij value. So based on that, we can find mixture Am constant like summation I, summation j, Yi, Yj, Aij. That is one way of doing that. Then there are more ways. If you don't want to do it like that, you can just do like we had assumed the additivity of volume for Bm, so we can similarly do for Am also. Then for this additive rule, sorry, for this geometric square root of Aij, it is found in literature that if you add this 1 minus Kij term, that is binary interaction parameters, always this Am is not accurate. So if you add this 1 minus Kij term, it gives better prediction. So this Kij is nothing but binary interaction parameter, and it can be so it should be Kij should be equal to if it is 0, then only this equation Kij can't be equal to 1. It should be always less than 1. So then only this Am will follow the equation. Okay, so there are two ways, Am, Bm. The very important thing to find out. So this was just about finding Am and Bm, but we have so many things coming up together, like CO2 and CH4 if we are considering. So we will have critical temperature of each component, critical pressure, critical volume. So how to incorporate all those things, because if you are solving any equation of state, then these critical constants are going to be part of that. So how do we deal with those critical constants in terms of mixtures? So for that, there are some equations. There are some from literature. There are various equations proposed, and based on the conditions, we can use those kind of equations. So first is by this some author Knapp et al. And this can be used for Lee-Kissler approach. So he assumes that TCM can be expressed by this following way: 1 upon VCM raised to 1 by 4 summation ij YI VCIG raised to 1 by 4 TCIG raised to 1 by 4. Okay, so this is the mixture critical temperature. Now, to find mixture critical temperature, we need to find mixture volume, then this TCIJ and VCIJ term. So those VCM mixture volume, it can be just simple additive rule from additive rule summation I YI YJ VCIJ, and this VCIJ is nothing but 1 upon 8 and VCI raised to 1 by 3 plus I or J means whatever number of components you have to do this, use this particular formula. Then similarly for omega eccentric factor, we simply use this additive rule, that is summation I yi omega I. Similarly for critical temperature, we use geometric mean square root TSI TC of one component, critical temperature of one component into critical temperature of another component. And from that, we can find the value of PCM, critical pressure of mixer. Okay, so this is one way. Then the other way is to use virial equation of state. Okay, I will show this virial equation of state. So virial equation of state was in two forms: pressure explicit form and volume explicit form. So if we virial equation of state was, I guess, in this lecture. So I will just show the equations. Virial equation of state for pure component. No, not in this one. I guess it is in this one. Yeah, this one. This is cubic equation of state that we are discussing right now. So when we were dealing with virial equation of state, it has this kind of term that PV by RT is equal to 1 plus BP by RT. So this B is my interaction term. So if when I am dealing with low to moderate pressures, I can neglect higher order terms. BP by RT I have considered. Then if we go further, it will be something C into P by RT, like those kind of term we can ignore when we are dealing with low to moderate pressure. So how to find this constant B in case of mixer? So when if we remember, this BPC by RTC was defined in terms of B naught plus omega into B prime. So B naught is some separate relation 0.083 minus 0.422 TR raised to 1.6. Similarly, B prime also had similar relation. So for this virial equation of state, first thing is to find out what is the mixer B naught, what is the mixer B prime. And if we know the mixer B naught and mixer B prime and omega, we can simply use the additive term summation of yi omega I. Then TC also, we can choose any one of those above terms. Similarly for PC, so we can do that. So first thing is to find B naught and B prime, we need to know the mixer reduced critical temperature, mixer reduced temperature. So for that, okay, so how BMs are found? So BMs are nothing but similar, some additive rules, summation yi yj, bij. So from there we can find the value of BM. Now what was my equation? BPC by RTC was equal to B naught plus omega B prime. So those all B, P, T, B naught, omega and B prime all should be interaction with one or another molecule. So in that way, we have to write the equation. Now, now the first important thing is to know the B naught and B prime. So B naught was in when we were dealing with pure component, it was 0.083 minus 0.422 divided by TR raised to 1.6. So when we are dealing with mixer, so this TR mixer we need to find. So TR, what is TR mixer? TR mixer is, what is TR? TR is reduced temperature, that is nothing but T divided by TC. So TC mixer. So to find out TR, we need to know the mixer TC. So mixer TC is basically found as square root of TCI TCJ, and 1 minus Kij. Kij is nothing but interaction parameter. If you are taking Kij is equal to 0, it will be normal geometric mean. So if you know TCij, then from TCij, we can find the value of T by TCij. So that will be giving us TR value. So this B naught and B prime, we have solved how to do it. Now, omega is nothing simply but omega I plus omega j divided by 2. Now, the issue is with PCIJ. So how to express PCIJ? So it is better way to go from compressibility factor Z value, because when we are dealing with mixers are individual components are also non-ideal. So to find the mixer critical pressure, we need to do what is PP Z into R T by V. So for that, we need to find mixer Z, mixer T, and mixer V. So mixer Z, it is nothing but simple arithmetic means ZC1 plus ZT2 by 2. Similarly, TC we have already seen here, and VC is nothing but volume cube roots. VC I raised to 1 by 3 plus 1 plus 2 raised to 1 by 3 divided by 2. And when we take the cube, we find the absolute volume. And when we put this, we have the value of critical pressure. So this is how uh, we can find the mixer properties or mixer constants for virial equation of state. And similarly, earlier we had a look for various kind of equation of state also. Okay. So this was all about when we are dealing with mixing. It is very important to find the correct mixing rule or correct combining rule to correctly represent the system. So how can we do it? So there is no rule. So if you have some experimental data, you can use these kind of various combining rules, and you can see that for your system, which kind of combining rule or mixing rules are working best. Based on that, you can choose that for your system. Okay, so this was all about mixing. Now, when we are dealing with mixing, so here we have a very important term we have missed. We have already seen how to find AM, how to find BM, how to find those terms TC, TC mixer, PC mixer. So we are left with how to find a mixer volume. So for mixer volume, there is one law, Amigat's law for additive volume. So it just assume that you can just add the volume based on the number of moles. So it is nothing but summation of I, Ni, Vi. So Ni is my moles and Vi is my molar volume. So if you know the molar volume and if you know the particular moles, you just have to multiply and then add it. So that will give you the mixer volume. So that is what very simple Amigat's law, but this Amigat's law is going to be a very big assumption for upcoming path when we are dealing with ideality and non-ideality for mixers and solutions. So this assumption should hold true. Okay, so this Vm is summation I, Ni, Vi. So for ideal gas mixer, what is Z? Z is nothing but P into mixer volume divided by N into R into T. So that is very straightforward. So PRT I'm keeping constant, and VM I am replacing it by summation Ni into Vi. And then again, this Vi I can replace it with Zi into for particular component. What is this summation? This summation is for all particular components available in the system. Okay, so this Vi, so for particular each component Vi, we will have each component particular compressibility factor value. So for that each Vi, we can use Zi RT by P, and based on that we see that mixer compressibility factor is nothing but summation of Ni into Zi. Okay, but one more thing very important to note, that let's say I'm dealing my mixer at 350 Kelvin, that this Ni into Zi I should use at that particular 350 Kelvin only. So temperature pressure conditions should remain same when you're going from pure state to mixer. When you are using this all above rules also, temperature pressure conditions should be same. So Zi, if I want to find mixer Zi of CO2 CH4 at 350 Kelvin and 1 atmospheric pressure. So this Zi's should be calculated for pure components the same condition only. I cannot do add some other condition and I can find a mixer. That is completely wrong. So this Amigat's law of additive volume, this is approximate. It is not exact for real gas mixer, but when we are dealing with ideal gas mixers, this Amigat's law of additive volume holds true. Similarly, we have Dalton's law of additive pressure. So it is also similar. It says that P is summation of individual partial pressures Pi. So it says that pressure exerted by Ni moles of pure component gas I if it occupied the entire volume at temperature of mixer. So if we add those particular volumes, particular pressures, we get the mixer pressure. Based on that, if we know the particular pure component gas if it occupied the entire volume at the same temperature of the mixers. Okay, so that's how we can use Dalton's law of additive pressure, and this is also similar to this volume additive law by Amagat. This also holds true for ideal gas mixer, but it may not hold true for real gas mixer. So for ideal gas mixer, just to differentiate, earlier also we found the compressibility factor Zm, that is nothing but Ni/Zi or moles into Zi, mole fraction into Zi. Similarly, just to differentiate it from there, we have added prime. So Zm prime is it has no different meaning. It's just to differentiate from Amagat's law. So Zm prime is PV by nRT. So we can V by nRT as it is, and what can I write? P can be replaced with summation of Pi. Now if I in this V by nRT I keep inside, and if I multiply with Ni and Ni, so I get that Zm prime is nothing but Yi into Zi prime. So both laws both laws um, we are we are ending up at the same place. Okay, so and these both laws, those are only useful for ideal gas mixer. Those are very accurate for ideal gas mixer, not for real gas mixer. Now, to find these critical constants, TRM and PRM, use these to find Zm. Okay, so there is one law for critical properties. There is one law of K's rule. So it says that PCM, I can just use normal additive rule. So PCM is nothing but summation I j yi PCI. So whatever components I have to do y1 PC1 plus y2 PC2. It will give me mixer critical property, critical pressure, and when I want to find a reduced pressure, it is nothing but system pressure divided by critical pressure. So system pressure P divided by whatever mixer critical pressure I am finding from K's rule. Similar thing is applicable for critical temperature also. So critical temperature TCM is nothing but summation Ij yi TCI. So it is nothing but y1 TC1 plus y2 TC2. From that I find the mixer critical temperature, and then for to finding the reduced temperature, we just need to divide system temperature with just need to divide system temperature with our critical temperature. So that will give us mixer reduced temperature. Okay. Okay. So sometimes this critical temperature rule, this Y1 TC1 plus Y2 TC2 may not work for the mixture. So here we had seen for more than one components, we can use TC1 square root of TC1 TC2 we can do. Okay. So these may not always hold. These additive rules may not always um, be true, because this critical temperature pressure, these all are properties of interactions among molecules. So that's why we may not be able to always get very accurate results with simply using the additive rule. So based on that, these are some scientists who developed this mixer rules for critical temperature and critical pressure. So critical temperature, they kept it as it is, but critical pressure, they modified the expression by this following formula summation. They just replace this PC term with yi zci divided by summation yi vci into TCM. So these are various equations that can be used to find the various mixer properties. So this Zoff, it was for omega and mixer omega. That is nothing but simple addition rule. Okay. Now our main problem where we ended up last time, it was on fugacity. So we stopped it with we have learned this formula that RT ln F by P is nothing but integration 0 to P V minus RT dP. But when I am dealing with mixer, so when I was dealing with pure component system, I had simply written this formula. It is in this page, yes. Here. From, yeah, here RT, ln, sorry, yeah, RTLN F by P is nothing but integration 0 to P V minus RT by P dP. So this is when I was dealing with my pure component system, but I am now dealing with a mixture. So how to replace this F fugacity component of fugacity of pure component with fugacity of mixer. So we can just simply write F by Fm and volume by mixer volume. But how to deal with it? How can I go from um, individual component volume to mixer volume? So what is the, we have learned that when we are dealing with multi-component system also, the condition from chemical equilibrium or thermodynamic equilibrium is we should satisfy three conditions. Temperature of both the phases should be same, then pressure of both the phases should be same, and fugacity, or when we derived first in terms of chemical potential of each component in each phase should be same, and from that we derived that fugacity of each component in each phase should be same. Okay, so instead of doing mixer fugacity or mixer fugacity coefficient, can we replace it with something where uh, instead of doing mixer fugacity, we can write fugacity of particular component in that mixer. So that is what we have done. So it is RT ln phi cap. Phi cap meaning fugacity of component I in the mixer. This cap suggests that we are looking at the that particular component in the mixer. So RT ln phi cap is equal to RT ln. Similarly, Fm will be Fi cap by P is equal to integration 0 to P. Now I need to find the this particular quantity Vm. So, but we are looking at individual component, right? Individual component in the mixer. So that we can replace with del V del Ni at Tp and G not equal to I minus RT by P dP. So this del V del Ni at Tp and J not equal to I, this is called partial molar properties, or that is called partial molar volume. So how does it affect? So let's say you are having very large quantity of water. Okay. So in that large quantity of water, let's say you are adding 1 moles of water in it. So what is going to happen when I'm going to add 1 mole of water? So volume of the system is going to change, correct? So what should I expect? I expect that when I'm adding in large volume of water, let's say that volume is V, and I am adding 1 mole of water in it. So how should volume increase? Volume should increase in a way that my original volume was V, and if I add 1 mole of water, so the 1 mole of water has the volume of 18 centimeter cube. So my total volume should increase by 18 centimeter cube. Okay. So when I am doing this, when I am adding 1 mole of water in very large volume of water, so that increases also 18 centimeter cube of, so that is my molar volume of water. So that is correct. That is expected. But let's say I am adding 1 moles of water in very large quantity of ethanol. So what is going to happen? Uh, let's say my initial volume was V. This large volume of ethanol, it was containing the volume of V. And when I am adding 1 mole of water, 1 mole of water meaning 18 centimeter cube, its volume. So what should be my increase in ethanol case also? We expect that it should increase by 18 centimeter cube, but in reality it does not increase by 18 centimeter cube. It increases only by 14 centimeter cube. So what we are seeing here, we are seeing here that when I am adding water in environment of, when I am adding my 1 mole of water in large environment of ethanol, so the volume, molar volume, that is not similar to when I am adding water in large environment of water. So here it was my, here my volume change was 18 centimeter cube, and here it was my 14 centimeter cube. So component we are adding is water only in both the cases, but volume change is not same. So this is how, this is what is the issue when we are dealing with, when we want to find fugacity or fugacity coefficient, we have to deal with this molar volume, partial molar. So that is how we can deal. That is the answer to that question, that how to deal with it. So what is partial molar property? This is called partial molar property, that how much my volume is changing by adding particular mole. So that is dV, dNi, by keeping temperature, pressure, and n of j not equal to I, meaning other components concentration keeping constant. So that is what it is saying, that when I am adding 1 mole of water in 1 mole of water in very large quantity of water, how my del V volume is changing with respect to del Ni by addition of 1 mole of water with respect to how earlier I had volume, large volume of ethanol. So del B, how my volume, that volume is changing with respect to addition of del Ni, one component, 1 mole of water. So that is what is called partial molar property. So how can we define partial molar property in terms of concept? So partial molar property, it is a measure of how much the total property changes when Ni is changed. So that is what we are saying in case of volume, how much my total volume is changing when Ni, let's say, when the moles of ethanol or moles of methanols are added, by keeping temperature, pressure, and other mole numbers fixed. So this is how partial molar property is very important when we are going to deal with mixer properties, when we are going to deal with mixer. So what does partial molar property show? So partial molar property shows the contribution that a component of a mixer makes to the total property of the mixer. So that one addition of 1 moles of water when we are adding in ethanol, so how my total property of mixer is changing. So that is what we can learn from partial molar property. So in general, partial molar properties, when I'm going to define partial molar properties, I have to add bar on the system. So when I'm writing yi bar, so yi barring meaning partial molar, whatever the y is, let's say y is my enthalpy. So partial molar enthalpy. So that is nothing but total enthalpy of the system divided by, or del H by del Ni, keeping temperature, pressure, and other moles constant. Okay. So earlier we have learned molar property. Molar property means property per mole, and partial molar property meaning property, how property is changing, how total property is changing when we are adding some components. So that is partial molar property. So we know that molar property can never be negative. It is always, always, always positive. But when we are dealing with partial molar property, so it can be either positive or it can be negative based on the nature of the system. And when I am dealing with pure substance, so pure substance, it is just reduces to molar property, because for pure substance, there is nothing else. So it is only that component. So for pure substance, it is just molar property. It reduces to molar property. Now we have learned so many thermodynamic equations, that U is that G is H minus Ts, A is U minus Ts. All those things we have learned. So those equations can also be used for partial molar properties, that my chemical potential or G was H minus Ts. So I can also write Gi bar as Hi bar minus T into Si bar. A was U minus Ts. So I can also write that A bar is equal to U bar minus T into S bar. So this all partial molar property those all thermodynamic equations, thermodynamic functions for simple components, those we have developed, those all formulas are analogous for partial molar properties. And we have learned Maxwell relations in this lecture. So all the Maxwell relations that we have developed for pure component, that can also be applicable for partial molar properties. So here we have del T del V at constant entropy is equal to del P del S at constant volume. So the same thing is also applicable for when I am dealing with partial molar properties. Okay, so how can we define partial molar property? So very important thing to know that partial molar property Vi bar is del V del Ni, but that should be at always at constant temperature, pressure, and N of J not equal to I. Similarly, Si bar is equal to del S del Ni at Tp and J not equal to I. And Hi bar is del H del Ni at Tp and J not equal to I. And Gi bar is nothing but del G del Ni at Tp and J not equal to I. But we know that this del G del Ni at Tp and J not equal to I, it is nothing but chemical potential of the system. So this partial molar Gibbs free energy Gi bar is, it is nothing but chemical potential of the system. Only for Gibbs free energy part, because Gibbs free energy mu was defined in case of constant temperature, pressure, and these partial molar properties are also defined at constant temperature, pressure, and moles. Okay. Okay, so we have developed this relation in earlier classes. G is H minus Ts. So similarly, I can write that del G del Ni at Tp and J not equal to I is nothing is equal to del H del Ni Tp and J not equal to I minus T del S del Ni at Tp and J not equal to I. I am just differentiating, or I am just adding some moles of water, and I am seeing how G, H, and S are varying. So this formula we have applied. So it is nothing but basically Gi bar is Hi bar minus T into Si bar. Okay. So let's try to see what Si bar will give us in terms of chemical potential. Okay. So Si bar we have defined as del S del Ni at Tp and J not equal to I. So my del Ni. Now, how can I write my S? So S can be written from Maxwell relation as minus del G del T. S is minus del G del T at constant pressure. So that is what I will write. Instead of S, I am writing minus del G del T at constant pressure and N of G not equal to I. Now, these all equations, they follow the Maxwell rule. So I can interchange the differential with respect to what I am differentiating. So I can just write, instead of this, I can write minus del T and del G del Ni. And what is del G del Ni? Del G del Ni is my chemical potential of component I. So that is what it is. So what is my partial molar entropy? Partial molar entropy is nothing but minus of del mu by del T. Partial molar entropy of component I is the change in chemical potential of component I with respect to temperature with negative sign. Similarly, when I am dealing with partial molar volume, so partial molar volume is del V del Ni at Tp and G not equal to I. So how can I replace volume? So volume can be replaced as del G del P at constant temperature from Maxwell relations. So volume is del G del P at constant temperature. Then same, we are just interchanging this denominator part. So I'm writing del P at del G del Ni, and del G del Ni again it is mu I. So what is my partial molar volume? Partial molar volume is del mu I by del P. And partial molar entropy was minus del mu I by del T. One was with respect to temperature, and other quantity was varying with respect to pressure. Okay, so this is how we can relate S and partial molar entropy and partial molar volume with respect to chemical potential of the system. Okay, so now to go into deep for these partial molar properties, how to calculate partial molar properties. Let's say I am having V1 and V2. So what will be the mixture volume? And it is not going to be uh, addition just like water, the water had when we added 1 mole of water and ethanol in ethanol, and it was not the same change. Okay, so for studying this, we were at, yeah. So we have to look at page number 113. Okay. So from here, we will first derive the equation for that. So for any partial molar property mi bar, I am defining it as del nm by del ni at Tp and J. So n is my moles and m is my molar property. Okay. So pure species property I am defining. So mi is my del nm by del ni at Tp and G. So what I am seeing, this nm is my function of temperature, pressure, n1, n2, up to what many number of components we have. So let's say we are just dealing as of now with binary system. So can I write total differential of nm, which is function of Tp n1, n2. So I can write total differential dnm is equal to del nm by del t dt, keeping p n1 n2 constant, plus del nm del p, keeping t n1 n2 constant, into dp, plus del nm del n1, keeping, now I am varying n1. So uh, n1 can't be kept constant. It is as simple as that. So I will be varying temperature, pressure, and n2 dn1 plus del nm by del n2, keeping temperature, pressure constant and n1 constant, other component constant dn2. Okay. So this is the simple relation. So what can I write from here? I can write from here that dnm is del nm del t dt del nm del p dp plus, now this can be for n number of components, right? So I can just write it summation I is equal to 1 to whatever number of components we have in our system, del nm del ni dni, and tp n of j, which is not is equal to I. So this is what I can write. Now we know that this del nm del ni at Tp and J, what is that del nm del ni at Tp and J? That is nothing but my partial molar property mi bar. So I can just replace this, these two terms remain as it is, del nm del p dp, del nm del t dt, plus this term we just replace it with mi bar. It is mi bar dni. Okay. Okay, so we stop here and we go ahead. So how can I define my mole fraction of any component? So mole fraction xi is ni moles of that particular component divided by total moles. So ni is nothing but xi into n. So if I differentiate this, what do I get? I get that dni is xi into dn plus n into dxi. Just the rule of multiplication when rule of differentiation in multiplication. So dni is xi dn plus n dxi. So can I replace this dni is equal to xi dn plus n dxi here? So I will put this into here. Similarly for dnm, how can I expand dnm? dnm is nothing but n into dm plus m into dn. Okay, so this n dm plus m dn I will put here, and this dni that was xi dn plus n dxi I will put there. So what equation I will have? I will have n dm plus m dn is equal to del nm del p dp del nm del t dt plus summation I mi bar. What was initially mi bar d ni. So mi bar dni. So dni I am just replacing with xi dn plus n dxi. Okay. Now we will do some separation that all components with n n in the multiplication I will keep one side. So if I keep n constant, so it is dm. From here n is constant. We have written t comma n constant. So n is constant. So del m del p dp minus del m del t dt. And here also there is one more term of n, that is summation of I mi bar dxi plus constants of dn. So dn has only one constant m, and the other constant is this mi bar xi. Okay, so this whole relation turns out to be 0. Now very important thing to know that when can this equation be 0? Let's say one coefficient is n, one coefficient is dn. Let's say I'm keeping that n is equal to 0. If I have n is equal to 0, means there are no moles of the system. So can we call it a system? There is nothing like system when n is equal to 0. So this can't held true. Similarly, when dn is equal to 0. So when we are dealing with dn is equal to 0, then we don't need to do anything. We are only dealing with pure system. Okay, so this thing, these two can't be 0. So what we are left with 0, then this coefficient, this dm minus del m del p no system exists when n is equal to 0. So we are left with these two equation. This term is equal to 0 and this term is equal to 0. When these both terms are simultaneously 0, then this whole equation will turn out to be 0. So my equation will be dm minus del m del p dp minus del m del t dt minus summation I mi bar into dxi is equal to 0. This is my one relation. And my second relation will be m minus I xi mi bar is equal to 0. So from this equation 5, what can I write? I can write that m is equal to summation xi mi bar. So what are we doing? We are relating partial molar property of each component with total property of the system. So let's say I am willing to find the total volume of the system. So it will be nothing but let's say I am having ethanol and water. So I need to know the mole fraction of ethanol water for sure, and I need to know the partial molar volume for ethanol and water. So we see that it does not depend on one component. Total contribution of property does not depend on one component. It depends on both the components from this relation that m is equal to summation xi mi bar. When we added 1 mole of water in very large quantity of water, nothing happened. But when I added 1 mole of water in large quantity of ethanol, so ethanol has some effect. That's why the uh, total volume was coming out to be different. So this relation is very important, and this relation is called summability relation. Now we will come to this part. We know that dm. Okay, we have this equation that m is equal to summation I xi mi bar. So can I differentiate this equation? So I can differentiate it as dm is equal to summation I mi bar dxi plus summation I xi dmi bar. Okay, so if I add dm is equal to this differentiation mi dxi bar plus xi dmi bar here. So these terms cancels out. So I am just left with xi dmi bar summation of I for all components xi dmi bar minus this relation remains as it is del m del p dp minus del m del t dt. This equal to 0. Now when we are dealing with thermodynamic equilibrium, temperature pressure remains constant. So these two terms are going to be cancelled out. So we are only left with summation xi dmi bar is equal to 0 at constant temperature and pressure conditions. So this summation xi dmi bar is equal to 0. This is called Gibbs-Duhem equation at constant temperature and pressure when we are dealing with partial molar properties. We have also derived Gibbs-Duhem equation in other forms when we are dealing with pure component systems. Okay, so takeaway message from this is we need to, when I am mixing two things, I need to know the partial molar properties of each components to know the what will be the total effect, and it should definitely follow this Gibbs-Duhem relation. This will be equal to 0 when we are dealing with constant temperature and pressure. So in general, what we have defined that partial molar property of component I is nothing equal to del Nm del Ni at Tp Nj. We derived summability rule, that is m is equal to summation I xi mi bar, and we derived Gibbs-Duhem equation, that is summation I xi dmi bar, which is equal to del m del p dp plus del m del t dt. And when we are dealing at equilibrium conditions, constant temperature, constant pressure, this summation xi dmi bar will be equal to 0. Okay, so this shows, we already discussed that this shows that the partial properties of species making up a solution are not independent of each other. So when we added water, ethanol, so it depends on both quantities, water and ethanol. It does not depend on only one component. Okay, so this was all about how to find total system property from partial molar properties in the component using summability rule, and it must satisfy Gibbs-Duhem relation. Now let's say I'm dealing with now I'm dealing with partial properties in binary solutions. So okay, so we have defined this, or we have derived this summability rule that m is equal to summation I xi mi bar. Let's say I'm dealing with binary system. So what will be my total m? my total m will be equal to x1 into m1 bar plus x2 into m2 bar. So m is equal to x1 m1 bar plus x2 m2 bar. So let's say I'm differentiating this equation again. So my dm is x1 dm1 bar plus m1 bar dx1 plus x2 dm2 bar plus m2 bar dx2. Okay. Now what was my Gibbs-Duhem relation? Gibbs-Duhem relation was that summation I xi dmi bar is equal to 0. So this means that x1 dm1 bar plus x2 dm2 bar is equal to 0. So from this equation, these two terms cancel out, x1 dm1 bar plus x2 dm2 bar. This is going to be 0 because of Gibbs-Duhem relation. So we have dm is equal to m1 bar dx1 plus m2 bar dx2. Now let's say I'm having a binary system. So composition of, let's say, one component I am fixing. So second component is automatically fixed. Mole fraction of one component I am fixing. So second will be automatically fixed because x1 plus x2 should sum up to the 1. So this equation dm is m1 bar dx1 plus m2 bar dx2. So let's try to reduce this equation to one variable. So we have x1 plus x2 is equal to 1. So if I differentiate this equation, dx1 plus dx2 will be equal to differentiation of constant 1 will be 0. So we have dx2 is equal to minus dx1. So we have dm is equal to m1 bar dx1 minus m2 bar dx1. So dm by dm will be m1 bar minus m2 bar into dx1. So what can I write? I can write that dm by dx1 is equal to m1 bar minus m2 bar. Okay. So let's try to further evaluate it. We had m is equal to x1 into m1. So I can replace my m1 bar minus m2 bar as dm by dx1. So let's try to find out something from here if we can do it or not. So we have m is equal to x1 into m1 bar plus x2 into m2 bar. So x1 I can replace it with 1 minus x2. So 1 minus x2 m1 bar plus x2 m2 bar, x2 into m2 bar. So m will be m1 bar minus x2 m1 bar plus x2 m2 bar. So m will be equal to m1 bar minus x2 common m1 bar minus m2 bar. So what can I do now? I can replace my m1 bar minus m2 bar with dm by dx1. So it will be dm by dx1. Here I will just write dm by dx1. So what can I find? My partial molar property of component 1 will be equal to m1 bar will be equal to m plus x2 dm dx1. Okay. Similarly, I want to find for m2 bar. So it will be nothing but just this. M2 bar will be m1 bar minus dm dx1. So like that, but let's try to derive it. So earlier, what did we do? We replaced x1 with 1 minus x2. Now let's try to do replace x2 with 1 minus x1. So m is x1 m1 bar plus x2 m2 bar. So x2 is 1 minus x1 m2 bar. So x1 m1 bar plus m2 bar minus x1 m2 bar again. So we are again left with m is equal to m2 bar plus x1 m1 bar minus m2 bar. So what is m1 bar minus m2 bar? Again, m1 bar minus m2 bar is dm dx1. So if I rearrange it, I find that m2 bar is equal to m minus x1 dm dx1. So what we do, we are finding, now we know the partial molar properties of component 1 and component 2 in the mixer. But we see that there is one differentiation term coming out to be, that is dm dx1. So what does these two equations graphically or actually represent? What do we get from these two equations? So let's say that I am plotting my m versus x1. M meaning total property with x1. So let's say I'm having this kind of curve. So when I draw the tangent to this curve, so this curve is going to intersect at 2 points. One at x is equal to not exactly, yeah, at x is equal to 0, it is going to intersect at some place, and at x is equal to 1, it is going to intersect at some place. So based on that tangent, when I draw the tangent, it will intersect. So based on that tangent, can I write my slope of this curve? So my slope will be dm dx1. So dm dx1 is equal to, I am calling this I1 and calling this intercept 1, intercept 2. So I can write dm dx1 is equal to change in y divided by change in x. So what is my change in y? So it is intersecting here and corresponding to this is my total property m. So m minus I2 divided by x1 minus 0. Okay, so that is my slope. This is how I can find my slope, that dm dx1 is equal to m minus I2 divided by x1 minus 0. So if I rearrange this equation, so it is x1 into dm dx1 is equal to m minus I2. So my I2 is equal to m minus x1 dm dx1. So what was my m minus x1 dm dx1? That was my m2 bar. Similarly, so what we are getting from here, if I am plotting this m versus x curve, so one intercept is going to give me the partial molar property of second component m2 bar. Similarly, for the other side, what will be my dm dx1? This slope will be equal to I1 minus m divided by 1 minus x1, correct? I1 minus this corresponding value m divided by 1 minus x1. This will be my slope. So 1 minus x1 is nothing but component mole fraction of component 2 x2. So I can write that x2 dm dx1 is equal to I1 minus m. So I1 will be equal to m plus x2 dm dx1. So what is m plus x2 dm dx1? That is nothing but partial molar property of component 1. So what did we learn from here? It is very straightforward thing that when we are plotting m versus x total property with varying mole fraction, we see that when I'm drawing the tangent to that curve, it is going to give me two intercepts, and two intercepts are nothing but partial molar properties. Thus, the tangent intercepts give directly the values of two partial molar properties. Okay, let's try to understand what is going to happen in extreme conditions. Extreme condition meaning my x1 tends to 0 or my x1 tends to 1. What does it mean when I say that x1 tends to 0? X1 tends to 0 meaning my other component is particularly present. So my m will be not going to be equal to m will be equal to m2 bar will be equal to my m2, and intercept m1 bar will be equal to m1 bar infinite. What does infinite sign mean? Infinite sign mean it is at very low concentration. X1 tends to 0 meaning we are dealing at infinite dilute concentration. Okay, so my m1 bar is equal to m1 bar infinite. For the tangent line, x1 tends to 1. So when it is just one component, so my m1 bar will be equal to m1 and my m2 bar is nothing but at infinite dilution concentration. Okay. So this is what we have got from this. This is M2, this is M1, and this is my M2 bar infinite, and this is nothing but my M1 bar infinite. So this is all very important thing because this is going to be useful further for partial molar properties. First, we define any partial molar properties, and all partial molar properties are defined at temperature, pressure, and constant number of moles of other components. Okay, so that is how we define partial molar property, and from there we derived summability rule, that is m is equal to summation xi into mi bar, and from that we derived Gibbs equation at constant temperature pressure. When we are dealing with constant temperature pressure, summation I xi dmi bar will be equal to 0. And let's say I'm not writing it in terms of constant temperature pressure, so it will be nothing but simply xi dmi bar is equal to del n del p dp plus del m del t dt. Okay. So this is my Gibbs equation. Now from that we try to derive how to find out m1 bar and m2 bar. So we find that m1 bar will be equal to m minus x2 m plus x2 dm dx1, and m2 bar is nothing but m minus x1 dm dx1. And when I am plotting my total property m with mole fractions x1, I am going to get some intercept. So that intercept is going to give me the value of partial molar property of individual component that we are interested in. Whatever property we are looking, that we can find from the intercepts. Okay. And one very important thing that we know from summability rule, that the partial properties of species making up a solution are not independent of each other. Though they both the properties depend on each components available in the system. Okay. Now let's try to move ahead with this equality of chemical potential in each phase should be same. This we can also derive from this. If time permits, we will see it today. Else we can keep it for other time. So now let's try to have a look at ideal gas mixture. What does it mean when I'm saying ideal gas mixture? So if I see here, or mixture of ideal gas does not mean that all components present in the system are behaving ideally, but mixture is behaving ideally. But here we are looking at mixture of ideal gas. We are not looking at ideal gas mixture. So mixture of ideal gas meaning I am combining some ideal gases and I am mixing them. So that will give me the mixture of ideal gas. So let's say I am saying that CO2 is behaving as ideal gas and CH4 is behaving ideal gas. So now I'm mixing CO2 and CH4 together. So what is going to happen for that ideal gas mixture? So let's try to first find out the partial molar volume for each component in ideal gas mixture. So what can I write my V bar? V bar is equal to del NV del NI at Tp Nj. Correct? Now for ideal gas, what is going to be volume? Volume is nothing going to be N into I can replace V with RT by P. Okay. Now RT by temperature is constant, pressure is constant. Okay, so RT by P comes out and we are only left with del N by del Ni at TPNG. So what does this mean? Del N by del Ni. Del N will be del N1 plus del N2 plus del N3, and I am differentiating it with respect to particular Ni. So this differentiation is going to be 1. Okay, so we are left with V bar is equal to RT by P. So what was RT by P? RT by P was our ideal gas volume only. So what we learn from this that Vi bar of ideal gas is equal to RT by P, that is equal to Vi of ideal gas. So what does Gibbs theorem says? So Gibbs theorem says that a partial molar property except volume of a constituent species in an ideal gas mixture is equal to the corresponding molar property of species as a pure ideal gas at the mixer temperature, but at the pressure equal to its partial pressure in the mixer. So let's try to understand this first. The partial molar property of a constituent species in ideal gas mixture. So Mi bar in ideal gas mixture corresponding mixture is equal to the corresponding molar property Mi. So partial molar property is going to be equal to molar property, but when at same temperature, but pressure is equal to partial pressure in the mixer. Okay, so I can write that Mi bar ideal gas of temperature pressure is equal to Mi of ideal gas at temperature but pressure is equal to its partial pressure, and this is not true for volume. We have already seen that partial molar volume of component in mixture is equal to Pi of ideal gas only. Okay. So this was about that. Now let's just try to very quickly go through what is partial pressure. We know that what is partial pressure. Partial pressure of species I in an ideal gas mixture as the pressure that species I would exert if it occupied the if it alone occupied the volume of the mixture. So what can I write? Pi is equal to its mole fraction Yi into the total pressure of the system. So that is the pressure exerted by particular component or particular molecule in the system. That will be its partial pressure. Now let's try to have a look based on this definition that Mi bar ideal gas at Tp is equal to Mi ideal gas at Tpi except for volume. So let's try to find out some properties. Let's start with enthalpy. So based on this relation, what can I write? Hi bar ideal gas at temperature pressure is equal to Hi ideal gas of temperature and Pi. Okay, so this is what we wrote. But in lecture 2, I guess it is open. Yeah, in lecture 2, we have seen this thing that enthalpy, sorry, where does it go? Yeah, when I'm dealing with, okay, here I have only written, here we have written for enthalpy. Now when I'm dealing with enthalpy. Now we are talking about ideal gas. So when I'm talking about ideal gas, what is it going to be? Del V del T at constant pressure. It is going to be R by P, V by T. So this term is going to be zero. So for ideal gas, enthalpy only depends on temperature. It does not depend on pressure. Okay, so this HI bar ideal gas at temperature pressure is equal to HI ideal gas at temperature PI based on Gibbs theorem. But for any ideal gas, pressure is not going to be dependent on enthalpy. Enthalpy is, sorry, I spoke reverse. Enthalpy is not going to be dependent on pressure. So we just have HI bar ideal gas is equal to HI ideal gas. Okay. So individual enthalpy is equal to same when we are using um, partial molar enthalpy. So if I am mixing CO2 CH4, I will have CO2 and CH4 enthalpies as pure state and CH4 and CH4 and CO2 enthalpy in ideal gas mixture state. So those both are going to be same. So I can just find out my mixture enthalpy by using summation rule, summation yi hi. Okay. Now, if I go for internal energy, so similar relation for internal energy, Ui bar Ig at temperature pressure is equal to Ui Ig at temperature, but it's partial pressure. Now, similar thing we have observed for internal energy also. The du is function of temperature volume. So du is nothing but TdS minus PdV. So TdS is, if I replace this equation, so I get that du is CVdt plus T del P del T constant volume minus P dV. Okay, this is TdS term. So this we have seen earlier, so I will not spend time. So if I replace this term for ideal gas, so this term is going to be zero. So for ideal gas, Cu is nothing but Cv dt, only that term. So we know that for internal energy of ideal gas is independent of pressure. So what I can write, internal partial molar internal energy of individual component at temperature pressure will be equal to uh, molar, partial molar, not partial molar, molar entropy of that particular component at ideal gas state. If I use summability rule simply, I can find the total internal energy of the system. Now, let's try to move ahead with entropy. So for entropy, we have to write that SI bar of Ig at temperature pressure is equal to SI Ig of temperature and pressure, its partial pressure Pi. Now, this thing is not going to be, sorry, for entropy is not independent of pressure. Entropy depends on pressure. So we need to derive. So what is the entropy change in ideal gas? This equation we have derived dSIg is equal to Cp dt by Cp by T dt minus R by P dP. This relation we have derived. Let's say I am dealing with isothermal conditions. So this term is going to be this term is going to be zero. So I'm left with DSI ideal gas is equal to minus R by P dP. Okay. So let's try to integrate it. So how should we integrate it? We have to, we have partial molar property at total pressure and individual property at its partial pressure. So let's try to differentiate it with respect to from PI, SI at PI to SI at P equal to minus R. Similarly, pressure should also be PI to P. So what will be my SI at P? So SI of ideal gas at T comma P minus SI of ideal gas at T comma P I is equal to minus R ln P by Pi. Okay, what is my P by Pi? P by Pi is nothing but mole fractions. Inverse of mole fraction 1 upon Yi. Pi is Yip. If we just replace it, it is nothing but and negative will cancel out. So it is nothing but R into ln Yi. Okay, so what do I know? I know that SI ideal gas at TPI is equal to SI bar ideal gas at TP. Okay, so SI at TPI is equal to SI bar ideal gas at TP, which is nothing but SI TP minus R into ln Y. And if we use summability rule, to find the total overall entropy of the system, that is nothing but yi si bar. So it is nothing but yi into this si tpi minus r ln yi. Okay. So this is how we can, it is not as straightforward as it was for internal energy, and enthalpy. Okay. Now, similarly, Gibbs free energy is also not going to be same because Z is H minus Ts. As H is not going to change, but entropy is going to change. So we have to derive the equation for Gibbs free energy. Okay. So let's try to do this for Gibbs free energy. So what can we write? Similar thing. Gibbs free energy Gi bar at Tp is equal to Gi at Tpi. Now, what can I write? Gi is Hi minus Tsi. So Gi bar, we have seen the properties of partial molar. We have seen the characteristics of partial molar property. All thermodynamic functions are also applicable to partial molar properties. So I can write down as Gi bar ideal gas is also equal to Hi bar ideal gas minus T into Si bar ideal gas. So Hi bar ideal gas remains as it is, T remains as it is, and what is Si bar ideal gas? Si bar ideal gas is nothing but this term S ideal gas Tp minus R into ln yi. Okay. So Gi bar ideal gas is equal to Hi bar ideal gas minus T into Si bar ideal gas plus RT ln yi. Okay. But we know that Hi bar ideal gas is equal to Hi from this Gibbs theorem only. So this Hi ideal gas minus T into Si ideal gas. So what is that? That is nothing but Gi ideal gas, and this RT ln yi remains as it is. Okay. So Gi bar ideal gas is equal to Gi ideal gas plus RT ln yi. But we know that what is Gi bar ideal gas? Gi bar ideal gas is del G del N at Tp and J not equal to I. But that same term is also equal to chemical potential. So what is this giving? This is directly giving me the idea of chemical potential. So mu ideal gas is equal to G ideal gas plus RT ln yi. Okay. Now, we have developed this relation dg ideal gas is equal to vdp minus sdt. We were dealing with constant temperature term, so this term is going to be 0. So we have dg is equal to vdp. For ideal gas, v is rt by p dp. Okay. So this is nothing but rt differential of ln p. So my gi ideal gas is equal to, how can we find this gi ideal gas term? So this gi ideal gas term is nothing but rt into ln p plus some constant, that is integration constant, at that will be depending on particular temperature and particular species. So we first derived Gi bar ideal gas is equal to Gi ideal gas plus RT ln yi, and we find that Gi ideal gas is nothing but RT into ln p plus gamma IT. So what will be my chemical potential? My chemical potential mu Ig is equal to some constant plus RT ln p plus RT ln yi. But it is in logarithmic summation, so logarithmic summations are multiplied. So RT ln yi into p. What is RT ln yi into p? That is nothing but RT ln pi. yi into p is partial pressure of that particular component. So my partial molar Gibbs free energy is nothing but some constant plus RT into ln pi, and that is nothing but equal to chemical potential. Okay. So this is all about Gibbs theorem. Let's go through that once again. So from Gibbs theorem, we found that partial molar volume of component I is equal to, for ideal gas mixture, is equal to its pure component volume Vi Ig, that is equal to RT by P. Then we wrote the Gibbs theorem, that is in word it is very difficult to understand, but in mathematical form it is easy to understand. Let's try to once again see this. A partial molar property of a constituent species in ideal gas mixture is equal to its molar property as a pure ideal gas at the mixture temperature, but pressure is equal to its partial pressure, and this is not holding true for volume. Okay. Now, Then we derived the equation for enthalpy. So partial molar enthalpy is equal to molar enthalpy only for ideal gas because enthalpy is independent of pressure. Similarly, partial molar internal energy is equal to internal molar internal energy because internal energy is independent of pressure. Similarly, partial molar entropy we cannot directly write that. So for that we derived a relation and we see that partial molar entropy is nothing but ideal gas entropy minus R into ln yi. Ideal gas entropy of that particular component minus we need to subtract this term minus we need to subtract this term R into ln yi. Okay. And now for Gibbs energy, Gibbs free energy, if we find it, Gi bar is equal to Giig plus RT into ln yi. Okay, and then to find this, what is ideal gas Gibbs free energy? So that we got is as RT into ln P plus some constant, and that is nothing but coming out to be RT into ln partial pressure of that component plus some constant that will give us partial molar Gibbs free energy. That is nothing but chemical potential. Okay. Now, okay. So, um, okay. Now let's try to move ahead. So, what in last class? Where did we stop? We stopped. We had derived. We here we were discussing that how to find the partial molar Fugacity. We found all the thermodynamic terms that internal energy, entropy, enthalpy, Gibbs free energy, all those things we find. Now, how can I find that term for fugacity? So let's try to derive. Can I just write? We have derived this summability rule that m is equal to summation xi mi bar. So can I just write this term for partial molar fugacity? Can I write that fm is equal to summation xi fi bar or not? So let's try to see that. So at constant temperature, we see that RT into differential of ln Fm is equal to Vm dP. This we have already seen. Okay. So now for molar volume or mixture volume, I can write that Vm is equal to Y1 into V1 bar plus Y2 into V2 bar based on summability. Based on the summability rule. So what can I write? RT into D ln Fm is equal to Y1 V1 bar dP plus Y2 V2 bar dP. Now, if I'm integrating this equation, so what is V1 bar dP? So V1 bar dP is nothing but RT ln D F1 cap plus V2 bar dP is nothing but RT ln D F2 cap. Okay, so component fugacity of component 2 in mixer and fugacity of component 1 in mixer. So if I differentiate, if I integrate this equation with some limits, lower limits for this mixer is some pressure P to its fugacity Fm. So this is nothing. RT will be cancelling out from both the sides. So we are left with ln Fm by P is equal to Y1 into ln. What is this going to be? As if it behaves pure. So this pressure, partial pressure of component 1, that is Y1 into P to F1 cap. So Y1 into ln F1 cap by Y1P plus Y2 into ln F2 cap by Y2P. So we get that Fm by P is equal to F1 cap by Y1P raised to Y1, F2 cap by Y2P raised to Y2. So we are not getting that Fm is equal to summation I yi fi, but we are getting that fugacity of component in mixture is equal to Fm by P is equal to F1 cap by its Y1P raised to its concentration Y1 into F2 cap by Y2 into P raised to its concentration Y2. So in short, what can I write? I can write that Fm by P is equal to, these are, let's say I have so many C component systems. So for all component, it should be just multiplied. So I can write that pi I is equal to 1 to C Fi cap by Yi into P raised to Yi. So this is how I can find the mixture fugacity or uh, fugacity of my mixture. Okay. Now similarly, so what will be my equation? My equation is RT into ln Fi cap by Via into P is equal to integration 0 to P for particular component Vi bar minus RT by P dP. Okay, so this was my relation from each particular component at RT ln Fi cap. Here it should be Yi. Fi cap divided by Yi into P. As we are not dealing with pure system, we are dealing with mixture. So it should be Fi cap divided by Yi into P is equal to integration 0 to P. This one is V1 bar or Vi bar minus RT by P dP. Now we know that we just found out that Vi bar of ideal gas is nothing but RT by P. So I just need to put here RT by P. So what is it going to be? RT by P minus RT by P. So this term is going to be 0. So I am just left with RT ln Fi cap by Vi into P is equal to 0. So when does R cannot be equal to 0? It is universal gas constant. Temperature we are not at absolute 0 Kelvin temperature. So this is also not 0. So this ln1 is 0. So Fi cap divided by Via into P will be equal to 1. So Fi cap is nothing but Via into P. So what is the difference between? So when we are dealing with ideal gas, mixture of ideal gas, we see that fugacity, fugacity of each component in mixture is equal to nothing but its mole fraction times the pressure Via into P. So what is, just to make one clarification, what is my Fi? Fi is fugacity of component I in pure state, and what is Fi cap? Fi cap is partial molar fugacity of component I in the mixture. Here word partial molar is very important when we are dealing with mixture. And what will be my mixture fugacity? Mixture fugacity will be nothing but Fm by P will be equal to F1 cap divided by Y1 P raised to Y1 into F2 cap divided by Y2 into P whole raised to Y2. So this will give me the value of mixture fugacity, and Fm by P is nothing but fugacity coefficient of mixture, that is also similar, and this term F1 cap by Y1 P is nothing but Phi1 cap fugacity coefficient of component 1, partial molar fugacity of component 1, and this is nothing but partial molar fugacity of component 2. Okay, so this is what we did. Let's quickly try to revise it, and after that we will take some sample problems based from where we left in last class. So, sorry. Okay, so in today's class, what did we learn? We learned first mixture. When we are dealing with mixer and we are going with ideal gas, when we are dealing with mixers, in case of using some equation of states like Van der Waals equation of state or some virial equation of state, how to find mixing rules and combining rules. Okay, so mixing rules are nothing but uh, those are mixer constants in terms of pure component constants. So there are two ways additive, assuming the additivity of diameters, and other is assuming the additivity of volume. So based on we can find the size, and we know that AM interaction parameters are more important than sizes. So AM is more important. So AM we found, and to find this Aij in terms of mixing parameter, we need to understand the combining rules. We can define in terms of arithmetic mean, or we can define it in terms of geometric mean. In which condition, which mixing rule or which combining rule to apply, that is not easy to answer. We need to do, or we need to, when we have some experimental basis, we can define or we can compare the data with experiments, and then we can see which combining rule or which mixing rule is more important, or which mixing rule or which combining rule is giving more accurate predictions that we can know. Then we also learned that for virial equation of state, that how to find mixer B naught and mixer B prime, and from that we can find the properties. Then very important thing, Amagat's law of additive volume we learned, that is Vm is equal to summation NiVi, and that is approximate for real gas mixers, but that is absolutely valid for ideal gas mixers. Similarly, we learned the Dalton's law of additive pressure. So this P is nothing but summation of Pi, and both equations end up to the same way. And this Dalton's law of additive pressure is also very accurate and valid for ideal gas mixers, but not for real gas mixers. Okay, then we learned some rules to find pseudo-critical constants, like reduced temperature in mixture, reduced pressure of the mixer, and we can use that to find the mixer compressibility factor Zm. Okay. Then we were stuck at the one point that we defined that fugacity coefficient of mixer phi m. Here it should be via, it's a mistake. No, it should not be here via, it should be here via. Okay. So ln phi m will be equal to RT ln Fm by P, which will be equal to integration 0 to P Vm minus RT by P dP. But as we are dealing with phase equilibrium, so for phase equilibrium, we need to know the fugacity of each component in each phase, so that we can simply replace by these I terms. So ln phi I cap, so partial molar fugacity of mixer will be equal to Fi cap by P, that is partial molar fugacity of component I in mixer divided, here it should be YIP, will be equal to integration of 0 to P partial molar volume we should know minus RT by P. So from there we move to partial molar properties, where we see that one moles of, when we, that very easy thing or to understand is when we add 1 mole of water into very large volume of water, the volume increase is 18 cc, that is corresponding to partial molar volume of water. But when I add 1 mole of water in very large volume of ethanol, also increase in volume is little. So this says that partial molar property is, it is the measure of how much the total property is changed when Ni is changed, keeping temperature, pressure, and other mole fractions fixed. And it shows the contribution to the component of a mixture that makes to the total property of mixer. Okay, and we learned some characteristics that molar property should always be positive, but partial molar property can be positive or negative. And then for pure substance, it reduces to just molar property, and all those thermodynamic functions for pure component, single component, those are analogous for partial molar properties, and Maxwell relations are also applicable. Then we found out that SI bar, partial molar entropy of component I, is equal to minus del mu del T, and partial molar volume is equal to del mu del P of particular component of interest. Okay, and here we at one place we need to know that when we are using this this what is this called? Yeah, this mixing rules and all those rules, we should be dealing with the same temperature and pressures at all places. Not for these terms, but let's say if you are finding Zm prime using this Darden's law, then Zi of pure components will be evaluated at same temperature and same pressure as at the condition where I'm finding my mixture mixer compressibility factor. Okay, then after that we sorry, after that, yes, so after that we had a look at this partial molar property definition that we derived, that Nm del Nm by del Ni at constant temperature, pressure, Nj. And then from derivation, we find that summability rule, that M is equal to summation xi mi bar. But now we know that the summability rule is not applicable for fugacities and fugacity coefficient. I cannot write fugacity of mixture is equal to summation I xi fi bar. That is not true. That we had a look, or we will again see shortly. Then we derived Gibbs relation at constant temperature, pressure, that xi dmi bar is equal to 0. Okay, and if not constant temperature, pressure, then it is xi dmi bar is equal to del m del p dp plus del m del t dt. So this shows that the partial properties of species making up a solution are not, these are not independent to each other. Then we learned about partial molar properties in binary solutions. So we found that m1 bar is equal to m plus x2 dm dx1 and m2 bar is equal to m minus x1 dm dx1. And from there, when we plot m versus x1, so from tangent we find two intercepts I1 I2, and those two intercepts give us the value of partial molar properties in the mixer. Okay, then we had a look at Gibbs this thing, sorry, where did it go? Here, ideal gas mixer model. So where we find it, Vi bar at ideal gas is equal to Vi of ideal gas mixer partial molar volume of component I in ideal gas mixture is equal to molar pure molar volume in ideal gas, that is nothing but RT by P. And we learned Gibbs theorem that says that Mi bar at ideal gas is equal to Mi at ideal gas, but at same temperature, but pressure is equal to Pi. And this is not holding true for volume. Then we learned how to find enthalpy, internal energy of compound partial molar enthalpy. So that is nothing but pure or just we can say molar enthalpy of ideal gas because it is independent of pressure. Similarly, internal energy also it is same, but entropy and Gibbs free energy are different. So we found that entropy, partial molar entropy of component I in mixture is equal to SI if it were in ideal gas at Tp minus RLN Yi. And Gibbs free energy, it is nothing but Gh minus Ts. And from there, we find that Gi partial molar Gibbs free energy of component I in ideal gas is equal to its pure component Gibbs free energy GiIg plus RT Yi. And then we try to find out GIg. So GIg, we end up with RT into lnp plus gamma of E that is dependent on temperature, because here we are dealing with constant temperature. At particular temperature, we want to find this. So this, and when we add these summations, when we add these two relations, we find out partial molar Gibbs free energy, that is nothing but chemical potential of component I in ideal gas, that is nothing but RT into ln Pi plus some constant that is dependent on temperature and that is dependent on species. Okay. And then we had a look at very last thing, that is this partial molar fugacity that we can write. Can we write it? Fm is equal to summation xi fi bar. We cannot write it. We derived it that in mixer RT ln Fm will be equal to Vm dp, and for volume we can use summability rule, that is V1 bar, Y1 V1 bar plus Y2 V2 bar. And again, V1 bar dP is RT dln F1 cap, meaning fugacity, partial molar fugacity of component 1 in mixer and partial molar fugacity of component 2 in mixer. And when we try to rearrange, we see that fugacity of mixer Fm by P is equal to F1 cap by Y1 P raised to Y1, F2 cap by Y2 P raised to Y2. So that is also applicable for fugacity coefficient. And when we are dealing with mixture of ideal gases, so this Vi bar, we derived it. Vi bar is nothing but RT by P. So this term is going to be 0. So for mixture of ideal gases, Fy cap is equal to Yi into P. So this is all what we looked at today's part. So now let's try to continue from problems we stopped solving last time. Okay, so this one, yes. So we had completed the problems till 11. Okay, so now let's try to solve the problem 12. So problem 12 says that a 40 kg steel casting uh, of which Cp is equal to 0.5 kilojoules per kg Kelvin at a temperature of 450 degrees Celsius. So I have a steel casting of 40 kg and it is at 450 degrees Celsius, and I'm going to quench it in 150 kg of oil at 25 degrees Celsius. So my oil is at 25 degrees Celsius and its weight is 150 kg, and my steel casting is of 40 kg. Its temperature is 450 degrees Celsius. So we are assuming that there are no heat losses. So what is the change in entropy of casting, steel casting, change in entropy of this oil, and total entropy when we are adding up? Okay. So first thing, I have listed out this data that mass of steel casting is 40 kg, mass of oil is 150 kg, Cp of steel casting is 0.5 kilojoules per kg Kelvin, and Cp of oil is 2.5 kilojoules per kg Kelvin, and temperature of steel casting was given as 450 degrees Celsius. That is nothing but 450 plus 273.5 15, that turns out to be 723.15, and temperature of oil is 25 degrees Celsius, that is 298.15 Kelvin. Now from problem statement we are said that no additional heat losses. So what is going to happen, that steel casting is at 450 degrees Celsius. So whatever amount of heat that steel casting is going to lose, that amount of heat will be gained by oil. So Q of, sorry, here Q of oil gain is equal to minus Q of steel, minus sign because it is losing. So what is Q? Q is nothing but mCp delta T. So M is, I'm writing for Q of oil. So mass of oil, Cp of oil, delta T of oil, delta T meaning final temperature T minus initial temperature of oil TO is equal to nothing but minus QS. QS is mass of steel casting, Cp of steel casting into final temperature minus T of steel casting. So when it is equilibrium, we will have some temperature T. So if I put these values, 150 kg into Cp of oil is 2.5 kilojoules per kg Kelvin into T minus Cp of oil is 20. Here, as we are dealing with delta T, so it doesn't matter if I am writing in units of degrees Celsius. So T minus 25 is equal to minus 40 into 0.5 into T minus 450. So if I solve this, I get that my temperature, final temperature is 46.52 degree Celsius. Okay. So now I am supposed to find the change in entropy of steel casting first. So what will it be? My delta S of steel casting is equal to, what is entropy change, dq by T. So dq of steel casting divided by T. So what is dq of steel casting? Mass of steel casting, Cp of steel casting into dt. So if I want the value, so I need to integrate dt, and here it is already T, dt by T. And I will integrate from Ts, that was my initial temperature, to final temperature, some temperature T, that is 46.52 degree Celsius. Okay. So mass of steel 40, Cp of steel 0.5 kilojoules per kg Kelvin. Here unit consistency is very important. And when I am writing here, it should be, it is in ratio. So in ratio, it should always be in terms of absolute value. Okay. So temperature, final temperature, ln T by Ts. So what is T? T is 46.52 degrees Celsius. So I need to convert that value into Kelvin. So 46.52 plus 273.15. So whatever value I'm getting, divide by Ts. What was Ts? My Ts was 723.15 Kelvin. So if I put the value, I see that entropy of casting is reducing, that is coming out to be negative of 16.33 kilojoules per Kelvin. Now, similarly, I need to find the change in entropy of oil. Okay, so delta S of oil is equal to dq of oil divided by T. That is nothing but mass of oil, Cp of oil, integration T naught to 2 dt by T. So again, dt by T is ln T, and limit is T to T naught to T. So ln T by T naught. Mass of oil is given to us is as 150 kg. Cp of oil is 2.5 kg, kilojoule per kg Kelvin, and ln of temperature was 319. This temperature 319.67, that we converted into Kelvin, divided by TO. TO is initial oil temperature, that is 298.15 Kelvin. So if I put these numbers, I get that 26.13 kilojoules per Kelvin. Now we see that we have learned from the first law of thermodynamics that total entropy of universe always increases. So here what is happening, entropy, change in entropy of steel casting is, that change is reducing, or entropy is reducing for steel casting, but it is increasing of for oil. But when I am finding the total entropy change of the system, so what is it going to be? It is going to be delta SS, entropy change of steel casting and entropy change of oil. So if I add this, it is coming out to be minus 16.33 plus 26.13, that is 9.8 kilojoules per Kelvin. So what we are seeing here, that even if entropy of steel casting is reducing, but total entropy is increasing, so this process is a favorable process. Okay, so this kind of questions are really important, especially for gate. Those are asked. So you just need to apply the heat balance. You need to find the temperature. and then you just need to apply the second law of thermodynamics. Only one very important thing to remember here is your temperatures should be in the units of Kelvin when you are dealing in ratios. But when you are dealing with differences, it doesn't matter if you add it or not add it, because it is anyway going to cancel out. Okay. So entropy of steel casting is reducing and oil is increasing, and overall it is increasing. Okay, so this was one problem where we learned how to use. This is very basic thing that you know. We learned heat balance equation, how to use it, and we applied it to find the entropy change. Okay, next problem. Similar problem we have here, but in some different manner. Okay, we are saying that oil at 500 Kelvin is to be cooled at a rate of 5000 kg per hour in a counter current heat exchanger. What is counter current heat exchanger? Counter current heat exchanger is meaning hot is entering from this side and cold is entering from opposite side. So that is called counter current heat exchanger. And when we are dealing with co-current, so it is both same way. So what is the benefit when we are dealing with counter current heat exchanger? We find the LMTD, log mean temperature difference, that is higher, that is basically driving the heat exchange, that is higher. And if we are even going further, that is cross current, so it has even higher value of LMTD. Okay. Okay, so back to our original problem. Oil at 500 Kelvin is to be cooled at a rate of 5000 kg per hour in counter current heat exchanger using cold water available at 295 Kelvin. So I want to cool my oil from 500 Kelvin at a rate of 5000 kg per hour. And I want to cool it using some cooling water, cold water that is available at 295 Kelvin. A temperature approach of 10 Kelvin is to be maintained at both ends of the heat exchanger. So there is one important terminology, that is temperature approach. And we need to find the total entropy change of the process, and we are given Cp value. Okay, so let's first try to understand what is temperature approach. So how to define, sorry, uh, how to define uh, temperature approach in counter current heat exchanger. Okay, so this part so this TH out minus TC in is, it is called 10, and TH in minus TC out is 10. So this is called temperature approach. So what do we need to do? We need to develop this kind of first diagram for this problem. So what are we given? Oil at 500 Kelvin. Sorry, not here. Uh, okay, let's first try to gather the data. I am given the mass flow rate of oil, that is 5000 kg per hour. Temperature of oil as 500 Kelvin, and Cp of oil as 3.2 kilojoules per kg Kelvin. I don't know the mass flow rate of water, but I know the temperature of water, that is 295 Kelvin, and I know the Cp of water, that is 4.2 kilojoules per kg Kelvin. Now let's try to TH in to TH out. So I know that TH in, what fluid is entering at 500 Kelvin, but we don't know at what temperature it is going out. Similarly, TC in, TC out. So my cold fluid is entering at temperature of 290, sorry, 295 Kelvin, and it is going out at some temperature. So based on this, what was my approach? My approach is TH out minus TC in. So approach is given to us at 10. So this 10 is equal to first TH out minus TC in. So T1 minus TW is equal to 10. So what will be my T1? T1 will be equal to 10 plus 295. So that is 305. Similarly, T0 minus T2 will also be equal to 10. Temperature approach is given to us as 10. So T0 500 minus T2 is equal to 10. So T2 will be equal to 490 Kelvin. So one major problem, we know that both the ends of temperature, like in last problem, we were not knowing the temperature of this ends. But here in heat exchanger problem, we here know the temperature of both the sides. But we here what is not given to us, we are not given that what is the mass flow rate of water. So that is something we are supposed to find, so that we can calculate directly using heat balance equation, we with assumption that there are no heat losses. So heat gained by water is equal to minus of heat lost by oil. So heat gained by water, mw cpw, T2 minus TW is equal to minus heat is lost by the oil, so minus mass flow rate of oil, Cp of oil, that is T1 minus T0, final minus initial. Okay, so mass flow rate of water is not known to us. Cp of water is given to us as 4.2 kilojoules per kg Kelvin. Units are very important. Mass flow rate is in kg per hour. So Cp should also be in kg. It should not be in moles. This should be remembered. T2 minus Tw. T2 is 490. Tw, temperature of water is 295. That is equal to minus 5000 into 3.2 minus 5000 mass flow rate of oil into 3.2 into T1 minus T0, that is 305 minus T0, that original temperature was 500 Kelvin. So if we solve this, we find that mass flow rate of water is 3809.52 kilograms per hour. Okay, so our main problem is solved. So what were we supposed to find? We were supposed to determine the delta S total of this particular process. So how can we define delta S total of this particular process? Similar way, we will first find for water, then we will find for oil, and then we will add it. So my delta S process will be equal to delta S of water plus delta S of oil. When I'm going to add both these terms, I'm going to find the total entropy change of this particular process. So what is delta SW? Delta SW is equal to mass flow rate MW CPW integration TW to T2 dt by T, correct? TW to T2 dt by T plus mass flow rate of what? Oil, Cp of oil, integration of T of oil initial to final T1 dt by T. Okay, so what is it going to be? Mass flow rate of water is given to us as 5000 kilograms per hour. So 5000 Cp of water, that is given to us as 3.2 kilojoules per kg Kelvin into ln of T2 by Tw. So ln of 490 divided by 295. This one term. So if I calculate this one term, entropy change of water, so that is coming out to be 8118 kilojoules per Kelvin. Okay. So what we are seeing, entropy change of water is coming out to be positive. Now, if I find the entropy change of oil, that is nothing but mass flow rate of oil, Cp of oil, integration T0 to T1 dt by T. So mass flow rate of oil is nothing but oh, I made a mess. 490. No, actually, I have written it in reverse manner. It is correct. This was for oil and this was for water. Okay, so for oil, it is entropy change in oil is positive, and this entropy change in water. So mass flow rate of water, I have written it reverse. It is correct. 3809.52 into Cp of water, that is 4.2 kilojoules per kg Kelvin into ln of T, what is the final water temperature? 305 divided by 500. So if we say, we see that entropy of water is reducing, but entropy of oil is increasing. So what we are supposed to see, we are supposed to see the total change in entropy. So when we add these both the terms, we see that total entropy change of this particular process is increasing, and that is coming out to be 208.8 kilojoules per Kelvin. So from these two problems of today's class, we learned that when we may not be given one temperature, or if it is some kind of heat exchanger problem, we may be given temperature, we may be given mass flow rates on, or in this kind of problem where it was slightly tricky that you should know the temperature approach, that is 10 Kelvin. So that kind of data is given. So from that data, you are supposed to find the temperature or you are supposed to find the mass flow rate. When you are finding it, then you just need to apply the entropy equation, that is dq by t, that is mcp dt by t. And you just need to find the entropy change of individual systems of, in first case, steel casting and oil, and in second case, it was water and oil. And we will see that entropy of one system is going to reduce, entropy of other system is going to increase. But when we are going to add both, the total entropy of process, overall entropy of the system is always going to increase. So this is all for our today's session. So thank you so much, everyone. And if anyone is having any query regarding to the concepts of chemical engineering, thermodynamics, please feel free to write me on this particular email ID that is shown on the screen. I will try to get back to you as soon as I can. Thank you so much.